What do the words quantum computing mean to you? Maybe you picture a computer in the traditional box shape, but much larger than your laptop or desktop. Maybe you see a flashing lights and a spinning physics-type object inside, although those would be very reasonable guesses. Quantum computing is altogether different compared to today's computers. Visualize a large upside-down light bulb with the most elaborate filament you've ever seen. Rather than a thin single strand of metal, you see silvery layers wound tightly around a core. The layers narrow as you move down from the top. The structure is separated by golden plates. The outer part of the computer is referred to as the chandelier, a supercharged refrigerator that uses a liquefied helium mix to cool the computer's quantum chip down close to the coldest temperatures theoretically possible. Absolute zero. The incredibly cold temperatures allow the superconducting circuitry to assume their quantum properties. The properties themselves are what enables the computer to calculate tasks that would be essentially impossible on today's classical computers. Traditional computers work in bits or binary. Billions of transistors that process data on your computer are either on and appear as a number 1 or off and appear as a 0. Classical computers are extremely reliable in most cases because they adhere to relatively inflexible rules. This advantage is actually a disadvantage for certain problems where there are many possible yet only one true answer, such as the classic needle in a haystack problem. And this is where quantum computers stand out. Think of the classic arcade game Pac-Man or a mouse running through a maze. A classical computer navigates through by attempting every path until it finds the solution. Quantum computers determine the answer by replacing the bits of classical computers with what's known as qubits. The qubits are driven by the laws of quantum mechanics, the theory that physics works different at the atomic and subatomic scale. They calculate the probability that each solution is correct, rather than evaluating every single possibility. Traditionally, quantum mechanics is demonstrated by shining a light through a barrier with openings. Some light travels through the top opening, some light travels through the bottom opening, and the light waves collide into each, and in doing so create interference. Now, picture dimming the light until you're firing one tiny light particle, photon, at a time. Each photon must travel through one opening and they have nothing to interfere with on the other side. And yet the interference pattern still appears. This is known as the quantum state of superposition. Until you actually see the individual photon on the screen, each photon is in the state of superposition. It's as if it's traveling through all possible paths simultaneously until the state collapses to the observer while revealing a single point on the screen. Qubits use superposition to perform highly efficient calculations. Similar to how you can add more transistors to your computer to extend its capabilities, you can increase the number of qubits in a quantum computer to increase its power. So how can its power be utilized in the real world? Think of numbers, prime numbers. A prime is a natural number greater than one that can only be divided by itself or 1. This operations, while relatively easy going forward, is very difficult in reverse. The difficulty in doing so forms the basis of the most popular form of encryption today. The RSA algorithm was discovered in the US in 1977 and stands for Rivest Shamir Edelman, the last names of the inventors of RSA. In 1997, the UK claimed to have discovered the algorithm 4 years before in 1973, but it was kept classified by GCHQ. The only way to decrypt an RSA-based key is by factoring the product of two prime numbers. And each prime can be hundreds of digits in length and thus practically unsolvable without knowing the answers beforehand. Enter Peter Shor in 1995, the mathematician who graduated from MIT and was working at AT&T Bell Laboratories, devised what's known as the Shor algorithm. The algorithm factors prime numbers regardless of size. This meant that one day, once quantum computers were available, Shor's algorithm could be used to hack literally every password in existence. In 2001, IBM designed a quantum computer with 7 qubits to demo Shor's algorithm. The qubits were atomic nuclei, which have differing spin states controllable by RF waves. Although the design was not scalable, it did prove that Shor's algorithm works in a practice setting. Up until early 2022, quantum computing remained problematic and extremely fragile due to the fact that quantum states are inherently extremely fragile. However, in January 2022, researchers at the University of South Wales achieved 99% accuracy rates using silicon-based quantum processors and current manufacturing techniques. Phosphorus atoms were introduced in the silicon chips using ion implantation, the same method used on all existing silicon chips. This ensures the quantum breakthrough is compatible with the broader semiconductor industry. This was achieved using a technique called gate-set tomography, developed at Sandia National Laboratories in the US and openly available to researchers and tech companies like Quantum One. It's not surprising that quantum computing is exponentially faster than the fastest traditional computers that exist today. But just how fast are they? Research indicates can process 9,000 years of data in microseconds. https://www.iflscience.com/quantum. Processor does 9000 years of work in 36 microseconds. 63995. Stop and think about that for a few moments. 9,000 years compressed to 36 microseconds. What does that sound like to you? Time travel, perhaps? How will the small business world change? All digital communications, email, online banking, online messaging, etc., rely on data encryption built into the devices and applications used to transmit and store data. This encryption is based on mathematical functions that secure data, protecting the data from tampering or espionage. In public key encryption, also known as asymmetric encryption, the mathematical functions rely on cryptographic keys to encrypt data and authenticate the sender and recipient. Public key encryption requires that each message use two separate but related keys. One is called a public key and the other is called a private key to protect data. The sender and recipient of the data do not share their private keys, while public keys can be shared without downgrading the level of cryptographic security.